the next bit, this is kind of my favorite portion of the chapter. We get into some of the, really the giants of thermodynamics. So Sadie Carnot might not look like much, born in Paris, military engineer, man of principle, whose life in those turbulent times alternated between high political position and prison. Fantastic. Graduating from the École Polytechnique in 1814, Sadie also joined the Corps of Engineers. So, so he was doing some hands-on things, but he was also doing, and he died at the age of 36.
Uh-oh, I got a year left.
Well, cholera, no fun. But here's what he came up with. Here's really what he came up with. And this is one of the just fundamentals of physics. And in fact, if you go, I love reading this because Richard Feynman, also a giant of physics, quotes Carnot. He also, this is kind of a side note, this will be on the test, C-R-N-O-T. He quotes Carnot, and there's another engineer. There's another engineer by the name of Shannon. So Carnot did basically worked on this thing called thermodynamic entropy, and Shannon worked on this thing called information entropy. And the math looks kind of similar. And I just had a paper published earlier this year on the topic, but and we might dig into it a little bit later in the course, but we'll see. So Feynman says that Carnot was one of only 2 engineers ever to make a fundamental contribution to science. It's a pretty big compliment. And he says Shannon is the other one.
He said it's also a pretty big insult to everybody.
Well, it's kind of an insult too. Yeah, that's a good point. That's a good point. But here's how it works. So in all of these engines we've looked at so far, and let me just remind you of the engines we've seen. That's an engine. So you've got something hot, something's moving, something's hot, the water's moving, this fire is hot, the pump is running up and down, and here's your steam, and away we go with the car. So in every single one of these engines we've looked at, something gets hot and then something moves. Okay. So what ends up happening, going into the system, is we're just going to call this Q1. That's the heat of the system. And remember, Q has dimensions of energy, which is going to, again, be mass times length squared over time squared, fundamentally. And then some other heat is going to come out. And we know, and we were talking about before, like where's the water go? Well, the steam gets colder. So this is the hot side, and this is the cold side. And then what comes out is some kind of work. And so again, this is W equals energy equals ml squared T squared. So this is heat, and this is work. And they're both energy, it's just that the work is moving. So just think, gears, pistons, whatever, some sort of mechanical thing. And on the hot side, you'll just imagine just steam. And then cold, out comes the water. Okay, so that's just the mock-up model of a heat engine. Now, and again, this is a great little segue.
Thank you. Yeah.
Good? Okay. All right. Good little segue, because we know that heat equals the specific heat capacity times the mass times the change in temperature. So let's just look at one like really simple example. Let's just make it super simple. And again, let's think about those earlier engines we looked at where this might look kind of weird. Like, oh, what kind of coffee cup is that? Well, the hot's coming out here, and you could like in here is some kind of turbine maybe, something extracted, and then the cold comes back down here, and underneath there's your fire, right? So somehow work is being done. The water inside isn't leaving the system. It's just, it gets hot going out the top, cold coming back in the bottom. So the mass, so the heat has mass, it is always the same. You're always dealing with the same mass. The steam goes up, and it's not leaving the system. So that hopefully that makes you feel better, Kat. You're not wasting any water. You're not just sending it out. Yeah, closed system. Yeah, okay.
What does that say where it popped up there?
This says steam.
No, up. Right there.
These
Yeah.
these are just little turbines. It's just some way of extracting work.
Oh, okay. Gotcha.
So W is work.
Yeah. Gotcha.
So the mass, so delta M over delta T, the change in mass over the change in time equals 0. It's not changing. The specific heat capacity isn't changing either. It's a constant. So if this is Q1 heading out, it also heads out at temperature 1. And if this is Q2 coming back, it's also at temperature 2. So we know that Q1 is greater than Q2. We also know that T1 is greater than T2. So we can just take this one equation, since these two guys are constant, we can just simply say that Q2 over Q1 equals T2 over T1. So the heat, the change in heat is proportional to the change in temperature. That's all it's saying. They're proportional. So if you tell me how hot it is, what the temperature is, I can tell you how much heat is in there. So that's step one. Now the kind of the breakthrough genius, if you will. It's just to say that let's just do it this way. The efficiency, there's that eta again, efficiency. The efficiency equals the, let's see here. Let's do it this way. Here, let me take one quick pause. I want to derive it. Actually, tell me if you can derive that equation really quick while I take a quick break to bust it out. Give me a second. Okay, I think I just got a little bit ahead of myself. I got a little bit too anxious. Here's the way it works. So the efficiency is equal to how much work we got out divided by how much heat went in. Okay, and here's the rub, because you're never going to get all of the heat out. First of all, because all of the heat would take it all the way down to absolute zero. To get all the heat out, you'd have to take all of the motion out of all of the molecules. Sorry, it just doesn't work that way. So this is quite good. So from there, we know that the work is actually just the difference. I can go ahead and write that out here. So the work equals Q1 minus Q2. Some energy went in, we took some mechanical energy out, and some thermal energy was shed back to the environment. Okay, now with that definition, yeah,
Sorry, I apologize.
not at all.
So would it be cold water going in and hot steam coming out? But no, because the heat coming in is what creates the work.
Yeah, I mean,
You just have cold
it
water.
could be hot steam coming out, but it would just, the hot steam coming out couldn't be as hot as the hot steam going in.
Yes.
Yeah.
So what about the cold water?
Cold water, I mean, that's kind of best case scenario. And again, it could loop, I mean, it could loop right back. So for example, I don't know if you heard the news this summer, but the town of Colstrip was being rationed a little bit on water because they had to pump so much from the river to keep the plant cold. So, kind of weird, but happens. Same thing, same reason you sell the nuclear power plants near bodies of water. What?
So you're putting in cold water to the system?
Well, you would charge it with cold water initially, but then in order to get it going, I mean, you gotta use heat. Something's gonna get hot, something's not necessarily gonna get burned, gonna burn. You could make heat with electrical resistance, which came from a solar panel. You could make heat directly from concentrated solar. You don't necessarily have to set something on fire to make it hot, is the point, exactly.
And water that's continuing on through circulation isn't necessarily cold at all. It could be room temperature or even...
Yeah, and cold is a relative term, and the whole point is you're never really going to get, well, the only way to get a fluid colder than ambient temperature is also to do work.
It takes energy,
Yeah.
We put it I read the greenhouse gas emissions for the university,
Yeah,
and it talks a lot about underground using the aquifer.
That's right.
For coolant, and
yeah, we do have a geothermal system at the university, but again, we're not cooling that water. The earth is cooling the water under the.
we're using the water to heat it up for our purpose, but then when we inject it back in, the temperature changes is 10 degrees.
That's right,
While
yeah.
we inject it, but it doesn't have any consequences or any impact on the water table.
In terms of affecting the water table's height, our pump and dump system does not. There might be other consequences of sending hot water back down to the table. Yeah.
You put something hotter in, I mean, you're messing with the soil. And
Yep.
And everything
Everything
that's running
else.
through, like
Yeah.
the equipment, you know what I mean?
Oh, yeah.
Yeah.
But, I mean, it does show that they're using like that technology, the underground, just to cool it. And they're looking at like quite a bit of profit and return, like after 8 months, they're already like making
Yeah.
their money back.
Yeah, that's right. That typically, you put the capital in to put the geothermal system in up front, and you're not spending it on.
Like the Davidson Honor Hall or whatever that is on main campus, they're completely like green. The whole building is, they've done that.
They do a pretty good job. Yeah, I mean, they're still they're not off grid. Yeah, I don't see the organic garden in the back of Davidson yet,
They're
but
putting in all
yeah.
like those new sensors and like room temperature reading, and everything's all automatic so that it can be more efficient.
Yeah. Brian Kearns, who's also on the energy tech faculty, does a lot of that. So, yeah. Cool. Okay. So now we've got the relationship. So the work is the heat in minus the heat out. So from there, we can just do a little algebra on it and say Q1 over Q2, or sorry, Q1 over Q1 minus Q2 over Q1 equals 1 minus Q2 over Q1 equals 1 minus T2 over T1. Okay, so that is the definition of efficiency. And when you were reading summary 2, there was a lot of talk about improving the efficiencies of coal-fired power plants. So let's just do one little example of a heat engine What's ambient temperature in Kelvin? What's our temperature right now?
I'm gonna say 32.
32 Kelvin?
No, it's
Let's-
too hot.
let's
That
ta-
seems too hot.
Let's take a look. Too hot? Let's take a look.
Because it was cold today, so I'm gonna say 21. Final answer.
21 Kelvin, we're sitting at 21 Kelvin. Let's just take a look here and see what happens at 21 Kelvin. There's a neat little,
Well, this is that one we had last time.
yeah, this is a good one. So if we can actually take the temperature scale here, and, okay, let's go down to 21 Kelvin.
Oh, God, I was thinking Celsius,
Let's
not
go.
Kelvin. I was thinking
Well,
C, not K.
let's go up to 21 Kelvin.
Oh, God.
The entire,
No,
the
right?
only, let's come up to a slightly balmier,
About 273 to yourself.
yeah, maybe 71 Fahrenheit.
That's what I was thinking.
Yeah, I think you're thinking Celsius, okay. But that's important. We have all these things we're gonna do in,
Oh,
This,
oh.
so.
You add 273 to your.
32 divide time.
yeah, I'm just gonna call it 300. You know, 80 Celsius is,
Fahrenheit.
Yeah.
I think you just add 273 to whatever your temperature is.
Oh, for
and
Kelvin.
that's what you get.
yeah, 273, that's right.
Oh, okay, I
Yeah,
see.
so
I was thinking-
one delta Kelvin
Thank you.
is the same as 1 degree Celsius. So there we go. And you'll notice also, there's no degrees symbol in front of Kelvin.
That's absolute.
It's absolute.
Isn't that because of absolute zero?
Yeah,
Is that-
absolute zero.
I was just questioning.
Yeah, that's it. Okay, so T ambient is approximately 300 Kelvin. And let's just say we have a heat engine. And let's run that thing at 600 Kelvin. And here's another kind of, I don't know, pet peeve, if you will. Someone might say, oh, it went from 40 degrees to 80 degrees. It's twice as hot. Oopsies. You weren't talking, right? It's like, it'd be like saying if I went from 25 years old, or like, let's just say I'm 21 and I'm now legal, right? And all of a sudden I'm 28. And it would be like starting from zero when you were 21. Like in terms of temperature, you wouldn't be
Like you're more legal at 28?
more legal.
Well, listen to
I
this.
think I see what you're saying.
The thing I'm saying is that it only makes sense to say something's twice as hot if you're on a Kelvin scale. And so it doesn't make sense when you're on any other scale. And it happens all the time.
Within 10 years of me doing my full circle, I've now come back to the exact same apartment complex 3 doors down from where I was when I first moved here.
Whoa,
Trippy, right?
that is tricky.
And my wife lives up in her house that we're selling. But it's like I feel like the Lion King,
It happens.
full circle.
It happens.
Oh,
Well,
circled life.
Yeah, 'cause it's like I started
You're
there,
gonna be eaten
and now
by
I'm
an
in
apex
here. It's
predator
like I
pretty
started
soon.
exactly where I was at 10 years ago. So it's like, what happened this last 10 years?
Missoula will suck you in like a vortex. Okay, so now we're at 600 Kelvin. So what's the efficiency of an engine that is running? What's the maximum efficiency that something's running at 600 Kelvin can have? So remember, eta equals 1 minus T1 over T2. Pretty simple. We just have 1 minus, oh, I got those backwards, sorry. Yeah, I typically think 1 is smaller, but 1 just means it's the temperature going in. You can define it however you like, but we'll just use the convention. So T2 over T1. And again, if you get confused, if you get it backwards, it corrects itself because the efficiency has to be less than 1. It has to be between 0 and 1. So if you get a number other than that, you're wrong, and just flip them. So there we go. So 300 Kelvin over 600 Kelvin. Kelvin equals 1 minus 0.5 equals 0.5. And so we've had this discussion a bunch. I don't know if I mentioned while we're talking about smart people. Here's our very own Steve Running.
Or taking this class?
Yeah.
1 of 3.
Yeah, so Running won the Nobel Prize, but he sort of asked me just sort of point blank there, like, Brad, why don't we make these coal-fired power plants more efficient? And I said, well, go talk to Sadie about it. You know, you can't. I mean, that's just, you could. I mean, you can make them hotter, but then things start melting and you get worse NOx problems. You have even more nitrogen combining with oxygen. But so the only way to make it more efficient is just to make it hotter. It's just that simple. You can't argue with it.
That reminds me of my little saying, the star is always far. You could always replace that star with one of your idols, like Sadie. He's far away in time, but his ideals could be re-implemented today.
Absolutely, yeah, absolutely. And the further we go on, the more of these Richard Feynman lectures get published. It's kind of, like sort of the further we go into the future, the further back we can see in time too. In a lot of ways, with our telescopes and even with our information. Like, oh, hey, I found the last archives of the Beatles or whatever. Now it's out there on anyway. Okay, so that is fundamentally important to really all of physics and all of thermodynamics. And the three laws. The three laws are these: delta E over delta T equals E dot equals 0. That's the first law. The next one is that delta S over delta T is equal to S dot is greater than 0. I guess before we get any further, let me just define what S is. What is S? What is S?
S is carrot guy. Isn't it? Carrot.
Yeah, so Carnot did not define entropy per se. There were some others that came along and took a shot at it. But S, the change in S, the change in entropy, equals the change in heat over temperature. And I just can't help it. I'm gonna do one quick thing. Oh, here it is, right here.
Entropy?
Entropy, there it is, ENTROPY. This is a paper of mine. Just came out last year. So here's what I was looking at. I was just looking at entropy, which is just this. This is all it is. It's just how much heat was exchanged at what temperature. Because it's happening all the time. Like right now, even sitting in this room, we're all heating the room. My laptop's heating the room. Coffee's getting cold, heating the room. We are entropicizing the air in here. We're making it more disorderly. And it's happening at some temperature. So what I try to do in this paper anyway, let's see if it gets cited much, but I say that the rate at which humans are entropicizing the planet is 10 to the 23rd greater than the universal background entropy rate. Because I just said down here, this is happening all the time. Heat is being exchanged all the time. The sun is shedding entropy, right? So this is greater than 0. The entropy of the So this plot's kind of boring. If you look at time here and energy here, it's flat. Now, there might be more radiation energy, there might be more mass energy. We already talked about Einstein. Mass is constantly being turned from mass into radiation. Sun's doing it 24/7, 365. The opposite can happen. Radiation can condense into matter, if you will. And in fact, that's kind of the theory on how the early universe was formed. It would just,
See, in
you know,
humans, we degrade over time as well.
yeah, I don't know how nuclear our little chemical cells are, but the point is, energy is being exchanged. That should be just a dead flat line between, among all of the energy types that we talked about in chapter 2.
Well, that's like the law of equivalent exchange, like you can't lose any mass or any.
It's this, yeah. This is the first law of thermodynamics, and the more complete form says that. And in this case, you're just calling energy mass is also energy. So yeah, matter and energy cannot be created or destroyed, just exchanged.
Right.
First law. Okay, but second law says that this happens. But the question is, what's the slope of that line? We already know the slope of this line is 0. Is it going up fast? Is it kind of like taking its time? What's the slope? Because you could imagine, well, even when you leave today, you're going to get on the bus, you're going to get in the car. If you, let's just say, get in your car and just floor it and like peel out and spray gravel and rubber and exhaust. I mean, the entropy rate is up here. You're entropicizing, just like shedding more heat more quickly, versus I'm just gonna tiptoe along, go stealth mode, not even disrupt a single pebble that's in my path. So you can see like two separate paths could have very different entropy rates. So here's atomic bomb. And here's just going in to like assassinate the leader or something, a little cleaner.
Or at the lowest level, just getting really frustrated and exerting a little more heat, getting mad at your home.
Yeah, here's mad at your homework, steam coming out. Here's just calmly getting through it. So that's the first law. This is the second law, and then the third law is kind of cool too. It just says that the temperature is greater than 0. It's just that if you try to make something absolute 0, some heat is going to leak in from somewhere. And the way to think of these, I love this, and I wish I could remember the name of the author. Some scientist said, you can't win, like you're never going to come out ahead. You can't break even. Right, so this kind of says the house is always going to win. You mentioned eventually when you die, your body's going to go somewhere. It's going to take you back. And then this one is you can't stop playing. You can never get to absolute 0. So just kind of a fun poker analogy. Okay. So there's that. There's Carnot. There's Watt. This is the diagram that I already showed you there. High temp going to low temp. This is on page 185. This is an example of what can go wrong. What can go wrong? We're actually now in figure 611. This is the path taken by the boiler after an explosion, circa 1890. So, again, as we already mentioned, in order to make something more efficient, you want this temperature to go up. Come on, make it more efficient. Why are we messing around? Well, when that temperature goes up, the pressure goes up, and then the safety valve that you forgot to install wasn't there, ruptures, and now you've basically made a rocket. Your boiler has turned into a rocket or a ballistic missile. And there it goes.
I extra shovel full of coal did us wrong.
Yeah, flying off. Flying off into the neighbor's yard. Okay, so here's Threvik himself, Threvithik, son of a Cornish mine manager, 6 feet tall, very strong, adventurous in his life, as in his engineering, and both were successes and catastrophes. So after his locomotives, we saw his car there, after his locomotives had come to grief, he returned to stationary machines. So failing to make money in Britain, he went to Peru as an engineer in the silver mines. There he prospered until a revolution forced him to leave the country, abandoning all his property. Penniless in Colombia, he met Robert Stevenson, who gave him his fare back to England, where he continued to generate ideas but no money. He died a pauper in Dartford. So there you go. Get your patents filed. Get your line of attorneys. Here's Stevenson, 1781 to 1880 or 48. Born in Wylam, Northumberland, where his father was a fisherman. Started work in the fishing business at the age of 10, but learned to read and write. Evening classes in 1812. Was appointed as an engine wright. So he's working on engines at a salary of £100 a year. $100 a year. I mean, it's only 10,000 pennies a year. Just bizarre, like what?
Mechanics, like diesel engine mechanics.
Yep.
So much.
Yep.
More than a lot of people.
His interests were not limited to trains. In a conflict over the invention of the miner's safety lamp, Sir Humphrey Davy called him a thief. Not undeterred, he continued his innovations, and by 1814 his locomotive was the first to use flange wheels, operating between the port and a city. Yeah. If you guys get a chance, go and watch some of Elon Musk's talks. He really talks about how, and again, these steam engines were driven by coal. We just mentioned that, England put its last lump of coal in a museum, and so right here is somebody who realizes if I don't get the fish from the ocean to the town in time, they rot, right? They're valueless. And if I have a bigger box of fish moving from the ocean to the town faster than the guy with the horse and wagon, my prices can be less, because I didn't spend as much time, and I didn't have to feed the horse, etc. So all of this is driving the economy in some way or the other. It's sort of speeding up the economy. I don't think this paper, and I try to make this point in this paper as well. Actually, it's the companion paper. It's this one. It's the 2016. See where I use the word socioeconomics? What I'm trying to show is that, so here's entropy, here's information, and to a large extent, money now is sort of just information. Like if you go and buy a stock on the stock market, you're like buying a piece of paper or a chunk of real estate. I mean, you're buying bits on a computer. So money and information have become highly intertwined. And so later on in this paper, I try to make the same point, is that now money and information are kind of the same thing. And you can see that in Elon Musk's models. He made his initial money, some of his first things was just an early version of MapQuest or Google Maps, and then it was PayPal, just online banking, money and information. But now what he's done, which is impressive, he's sort of moved himself from the money and information realm back into the mechanical, the physical realm, which is entropy. So what he's now doing is saying, we don't have to use fossil fuels to drive our economy anymore. We don't need to,
Masters the ebb and
we-
flow.
yeah, we don't need to make as much of this. We don't need to drive this entropy up with the pollution, et cetera, to make more of this.
But it takes that to be able to start it. and-
Absolutely, there-
and no one wants to do that.
Yeah, they do.
Well,
Don't say no one, Matt. That's negative.
Well, I can't say no.
I know, I'm just
But I
teasing you.
mean,
I'm just
like,
teasing
People with
you.
money, like, they don't wanna fork out the money for,
Yeah, they do. Bill Gates, billionaires,
well, I guess him and Zuckerberg did
they're
that.
forking it over for, yeah. So here's kind of the triangle, if you will, of money, information, and entropy that I've kind of tried to build in these papers. Because we really don't want entropy. Like, everyone wants to get richer, yay. Everyone wants to get smarter, yay. But do we really want the world to be more entropic and messier? Probably not. So that's kind of the balance or the tripod, if you will. Some people might say, oh yeah, let the world get messier, let the floods come so we can build the wall and shoot the movie Pacific Rim or whatever that was, But in general, you kind of want entropy to go down. So that's the tripod I'm trying to build there.
We also want people who are negative and want to drive the